It was fun like when I had a manual car, but like now that I have like an automatic, it's boring. So I just like
I wanted a manual, but I live on top of the mountains, and I knew that
yeah. If you don't learning on a mountain's horrible because then you'll roll back and then you'll just get scared and you'll burn inspection. And my mom directed me, so like I had to learn how to drive it because we didn't have she didn't have another car, and then my dad was like, I'm not teaching you, so.
Alright everybody, good morning.
Good morning.
Okay, so we got another long weekend ahead of us, right? And it's like, so we're going to try to finish up, or at least mostly finish up chapter 13 today. We're on electromagnetic induction, right? The idea that a changing magnetic flux through an area, which includes some sort of closed, well, it doesn't actually have to be closed, some sort of conducting material produces an EMF in the material. And I say it doesn't have to be closed. To produce a current, it has to be closed, but to produce an EMF, it doesn't actually have to be closed. We'll see an example of that in a little bit. But for the first two diagrams I have out here on the board, I would like you to take a few minutes to see if you can determine a couple things. So this is the current. I have a long straight wire. We kind of did this in class the other day. But I'm going to drop a metal ring such that the ring stays vertically oriented, right? So I've drawn it in two positions. I've drawn it above the wire, and then after it passes the wire. This is the first situation. The second situation is this. I have a coil of wire. Nevertheless, it's kind of hard to see how this is three-dimensionally oriented on a two-dimensional surface. But I want you to think of it as this is going, and so I'll do this in green. This is the direction of the coil. I want you to think of it as going into the board here and behind and then comes out. So it wraps around like this, and that's really kind of difficult to see with my simple graphics and on a two-dimensional surface. But the coil is oriented like this, so it comes in and then out and out. So that's what the coil is doing. I'm going to just move a bar magnet towards the coil. And so I'm going to ask you questions in both of these. In the first one, I would like you to tell me what the direction of the induced current is in both of these rings. And in this one, I'd like you to tell me what direction the current flows through the resistor, from A to B or from B to A. Right? So this is going to be, assumedly, a current induced here. And if you understand the geometry of how the coil is oriented and how the flux is changing, you should be able to see where the current flows. Now, this is a little bit more complicated than this one, so start off with this one. And then we'll see how we get on this, and we'll work both of them together as we finish up. And then we'll tackle this guy. So take about 10 minutes, work by yourself, work in groups if you want to. If you weren't here last time, find somebody who has notes and look on the notes. We've talked about how to do this. Just in brief, the first step is to figure out what the flux is. If it's changing or not, and if it is, how it's changing, and then what nature wants to do. Remember, nature always wants to counteract the change, so she induces a current to try to counteract that. So see what you come up with. I said 10 minutes, 6 or 7, and let's see what we can do. And I'm here to answer questions if you have. And it's not a quiz, you can talk to each other. if you
What are you getting? A question mark?
Motion is present. Because I think if it's going this way, and if it leaves, it's going towards the center. All I see is treat it like this one. Can you just treat it this one?
So wait, so that arrow is the current? Or is it or is the current being induced by that magnet?
I think it's being induced by the magnet.
Okay, so if that's the case, you got
And then this is the current. It's being
shooting
brought here.
south.
It goes towards the south. And then I would treat this as a straight, because if it coils, then I would just center.
Was it one of the flux? I think the flux
He
be
asked-
straight out.
He said, he was like, is it affecting, how is it affected? And then what's the direction of current in the water? I would think that it's,
It keeps looping around.
yeah.
Sounds good to me. So current still flows that way. Alright. What'd you get for these ones?
I was talking about outside here. Oh, for that thing right here?
Well, I'm kind of just guessing.
I could be completely wrong, but that's just like how I made sense of that.
Oh, so that's your magnetic field pointing to you.
Yeah.
The vector is going that way, so the force is going down. So to counteract that, you have to have a force going up, which would mean
Oh no.
How are we doing?
Yeah.
Let's see what we got.
Subpar.
So, who wants to venture an answer? If it's wrong, you always have permission to be wrong. I mean, not on exams, but that's the whole point here, right? What direction? Clockwise, counterclockwise? Clockwise. Clockwise. What about here? Clockwise. I don't know if this is right or not. We're going to find out together. What about here? Everybody has an answer? Yeah, we're trying.
I don't think so.
Okay. Alright, we'll do it. We'll figure it out. Okay, first things first. To figure out if there's a flux, we got to figure out what the field is doing. So, above this wire, what direction is the field?
Out of the board.
Out of the page. How'd you get that? For fields, right? Right-hand rule for fields. What's straight here? The current. So that's your thumb. Thumb goes into what's straight, fingers in tell you what the field is doing. Looks like it's wrapping around the wire, so that's coming out. Up here, going in, down here, right? And of course there are many more of those. I'm just drawing those too. This is going to form a circle like this. So, is there flux through this coil? Yeah. Is it increasing or decreasing? Increasing. Somebody justify that. Closer to the source means the field is getting stronger. Remember what flux is. Right? Where B is the magnetic field strength, A is the area of whatever you're looking at, theta is the angle between the B field and the area vector, and N is the sort of this general placeholder for however many turns of wire you have, right? In a lot of cases it's 1, sometimes it could be 6 million, right? But this is however many turns of wire you have. So you can kind of ignore this in a lot of cases. But the field strength is a big deal. So as this gets closer to the source, the field strength goes up. So the flux is increasing, right? What does nature then want to do? Decrease it. So the flux from a field coming out of the board, nature wants to decrease. How should she induce a field to do that? Into the board, right? She wants to decrease it, so she's got to counteract it. So she wants to induce, I'll do that in green, a field that looks like that, right? So here, the blue is should be a lot more of them, but this is the field from the wire. The green is what nature needs to induce in the coil. How should she induce a field in a coil? Well, the only way she can do it is to induce an EMF, which then produces a current. So what direction of current produces a field that looks like that? Clockwise. Again, right-hand rule for fields, right? Now my current is a little loop, so that's my fingers. Fingers are going to follow the direction of the current to produce this field. Although I would do it backwards, right, if I needed to know the direction of the current. The field is, in this case, is straight, so that's again my thumb. Into the board means the current has to be wrapping around like that. So clockwise is the answer. Okay. Any questions about how we did that? I should point out this is called Lenz's law. I didn't say that last time. Lenz's law is a series of things we're asking ourselves to figure out which direction the current is. Lenz's law is loosely stated, nature hates change, and she wants to counteract the change in flux, right? The actual induction is Faraday's law, but how we're figuring out the direction of current, loosely called Lenz's law. Okay. Questions about how we got that? Okay, same question here. What direction is the field? You've already told me. Into the board. This is the background field. What's it doing? Huh? Moving away from the wire. Yes. So what does that mean for the field? Decreasing, right? Field strength is lowering. So what does nature want to do? Increase it, right? She doesn't like change. So if the field is into the board, but the flux is decreasing, how does nature induce a field to try to build back up the flux? She needs to put it into the board, right? So now we're adding together instead of subtracting, right? So it's decreasing here. Nature again needs that field. We've already figured out that that's a clockwise current. So same current for different reasons. One is because the flux is decreasing, one is because the flux is increasing. But, and we get the same direction of current because notice the field has switched directions as well. Okay, questions about that? All right, where do we get stuck on the next one? So let me ask you the questions. Is there a flux through the coil? Is it increasing or decreasing? Okay, that's where we got. All right, so let's draw in a rude attempt at the field of the bar magnet. Right? Starts on north poles, ends on south poles. Although internal to the magnet, it connects those two. That's not language we use a whole lot, north and south pole, but it works. Yeah. All right. So if you look right here, the field is pointed into the coil or out of the coil? Into the coil, right? And is it increasing or decreasing? Well, as the bar magnet moves towards the coil, field strength has to be getting stronger, right? The coil is coming closer to the source. Closer to the source always means higher field, right? So The field strength is getting stronger and it's pointed into the coil. Therefore, the field strength is getting stronger. Therefore, the flux is increasing. Right? Nature wants to decrease it. So now, what does she need the induced field to look like? To the right or to the left?
To the left.
To the left, right? The field from the source is to the right. If nature wants to decrease it, she's got to put one to the left. That's going to look like this. Right? And this, it really is the field of a solenoid. I'd have to draw them a little tighter together, but that's the same idea. So, my field is straight. That's my thumb. Means my fingers tell me the current direction. So, the current looks like it's going into the board up here, coming out of the board down here. If I follow that around, that's going to be into, no. Yeah, so the coil is coming out of the board down here. Current's going into the board. Yeah, I got that right. So the current, this is a little tricky.
I think, did you mix up the dot and the X?
Say what?
Should the X be on top since it's going into the board?
Yeah, thank you. That's what happened. I mixed up my symbols. I did it right. Yeah, thumb in. Yeah, that's into the board. Thank you. Into the board, out of the board. Okay, that's a lot easier. Okay, so coming out, through, down, from B to A. So you see what I did there? I figured out that the current's going in, comes out, in, comes out, follow the coil, in, out, and then that's done. If you were to pull the magnet out, you would expect it to go the other way, because then the flux would be decreasing. Nature would induce a field in the opposite direction. I think the challenging one for these is the graphics. If I give you one of these problems, that will be professionally done
So is
graphics.
this one by nature?
But you
or
see
is
the
that
concept.
what's
You see
happening
what's
with
happening.
this? This one's by nature.
Any questions about this one?
No, it's fine later.
You're gonna be
The current direction. Yeah. So the current in the coil is moving in a circle. That's a
This
little
is
bit non-specific. Because
that way.
counterclockwise and clockwise
The field
depends on
must be
which way
pushing
you
it
look
up
at the
against
loop.
it.
So usually
the field is going that
bring
way.
it
So
down
that
here.
means
Say
your
what direction
current
is
is
flowing in
going
this
like
line?
this. So
All right.
if it's going in right
Other
here,
questions?
I understand that, but is
Yeah.
this nature induced or is this?
Yeah, okay.
this is what nature wants to
So
do.
the current's going to go around, back in, through, around, back in.
No, that's this right here. This part
Yeah.
right here, like you down here.
It's just the
Other
direction of
questions?
current.
Well, let's look at this one. This is an interesting example. So here is an example of, well, the situation is you have some sort of conducting apparatus, which is this big sort of sideways U-shaped thing. And then onto these rails, you slid some sort of conducting bar, which is free to move. And you've encased the whole thing into this background magnetic field, which is coming out of the board. And then, through some means, mechanical, you might be pulling on a rope, you might attach it to some, forces, I don't know, whatever. You're pulling the bar that way. So this velocity of the bar is coming from something external. So you have this background magnetic field, you have a velocity of the bar that's going out. So, where's the loop? Well, the loop is the conducting loop here, right? So, let's ask ourselves the same question. Is there flux through this loop? Yes. Is it increasing or decreasing? It's increasing. Now, here's the definition of flux. What part of that is changing to increase the flux? The area, right? This is the first example we've seen of something that has a changing area. That's not normally the case. Sometimes you'll see physics problems where somebody has a kink in a wire and they're pulling the wire and the kink gets smaller. That's another example of the area changing. But this is sort of somewhat artificial. These systems do exist. But the idea is the area is changing, which is not normal, but still possible. Okay. So is the flux increasing or decreasing? Increasing because the area is increasing. So what does nature want to do? She wants to decrease it. So the flux is increasing from a field pointed out of the board. What direction does the field need to be for her to decrease it? Into the board. So nature wants to induce a field that looks like that. You can just use your right-hand rule for fields. Some in the direction of the field, that's going to give me a current that flows through the bar like this, and then here and up through the resistor. Okay, so there's a couple things to talk about on this one. Number one, let's see if we can figure out what the actual induced EMF is. For that, we have Faraday's law, which says this. E, the induced EMF is equal to minus N dV dt. Where N is just the number of turns. This is my general expression. How many turns do I have here with my coil? I mean, just one, right? It's just two. It's a big structure, right? I only have one turn. But this is the general form. But when I write it down in just a second, the N is going to disappear because it's just one. Okay, so if I unpack now what the flux is, I get minus d dt, again, N's gone one, of what the flux is. B A cosine theta. Remember, theta is the angle between the area vector and the magnetic field. So let's figure out what the area vector is, right? Well, the area is on the plane of the board, so the area vector is coming straight out of the board. It's got to be perpendicular to the surface. So it looks like B is coming out of the board. The area vector is coming out of the board. What is the angle between them? 0. What is the cosine of 0? That's getting nice. So, a little blackboard algebra, let's erase that. Okay, so now, do you agree that the magnetic field is constant? Just a background field, right? So I can bring that out of the derivative. Minus B dA dt. Now, how might you, do you agree that the area is not constant, so this is not going to be a zero derivative, right? Because it's changing. That's the whole point of this. How might I express the area? Probably not dx, because I don't need to integrate it. But yeah, x times L is probably a good way to do it. L is not going to change, but what is changing is the horizontal position of the bar. If it's changing, make it your variable. And what I've done is I've set up a coordinate system such that my origin is here. And that way I can express the position of the bar anywhere as just x. So I can now write this as minus b. Area is going to be Lx, but we've already said that L is constant, it's just the length of the bar. I can bring it out. BL, and then what do I have left? dx dt. What's that? Yeah, this is the velocity of the bar, or speed of the bar, rather, because I don't have vector symbols. But same thing in this case. Yeah. Minus BL. So this is actually on your formula sheet, but this is where it comes from. I don't ever expect you to just plug something blindly into a formula, and if you can tell me where the formula comes from. But this is just a really